In this video, we consider the AR1 model and we derive the MA representation, which we will use in the next video to consider the properties of the process. So the AR1 model is given by yt equals a constant term plus theta multiplied by yt minus 1, and we have a shock or residual which we call epsilon t. Note that we could include other deterministic terms such as a time trend, but in this case we consider the simple model only with a constant. We have t equal 1, 2, up to capital T, so that's the sample size we have. Then we assume that epsilon t is IID with a mean 0 and a variance sigma squared. Typically we would assume that epsilon t is normally distributed, so that's just a white noise Gaussian process. Finally, we assume that the initial value, in this case we only have 1, y0, is given. Note that we need the initial value to start the process. Given the initial value, if we know the parameter values and we have observed epsilon t, then we could simply generate the time series for yt. So what we want to do in this video is derive the MA representation. And we're going to do that simply by recursive substitution. We start with the expression for yt. Yt equals delta plus theta yt minus 1 plus epsilon t. And then what we do is simply plug in for yt minus 1. We simply recursively plug in like that, and that's going to give us theta, a delta plus theta, and then we have delta plus theta yt minus 2 plus epsilon t minus 1. And then we have epsilon t from before. So now we have just substituted in from the model the expression for yt minus 1. We can rewrite this as 1 plus theta multiplied by delta. So we have the original delta here, and then we have an additional term here multiplied by theta. Then we get plus theta squared yt minus 2 plus, then we have epsilon t. We should not forget this epsilon here multiplied by theta. So we could continue like this. Do it one more step. We're going to get 1 plus theta multiplied by delta. Then we have theta squared, and now we plug in for yt minus 2. So delta plus theta yt minus 3 plus epsilon t minus 2. And then we have from before epsilon t plus theta, epsilon t minus 1. Let's write this out. We get 1 plus theta squared multiplied by delta plus theta to the power of 3 yt minus 3. And then we get the epsilon part, epsilon t plus theta, epsilon t minus 1 plus theta squared, epsilon t minus 2. Now we could continue like this, simply recursively substitute in the expression for yt minus 3, next for yt minus 4, and so on and so on. And we could do that once all the way back until we get to y1, which is the first value of yt. So if we do that, we would get 1 plus theta squared plus, and then we would get a sum all the way up to theta to the power of t minus 1 multiplied by delta plus, then we would have theta to the power of t multiplied by the initial value y0, and then we would have the part with all the epsilons, epsilon t plus theta, epsilon t minus 1 plus theta squared epsilon t minus 2 plus all the way to theta power of t minus 1 epsilon 1. So this is the MA representation. We now have an expression for yt in terms of a constant term, in terms of the initial value, and in terms of all the epsilons from t equal 1 up to observation t. So we have a decomposition here where we have 3 parts. The first part is the effect of the constant term in each of the periods. Then we have an effect of the initial value. And finally we have an effect of the shocks epsilon 1, epsilon 2, all the way up to epsilon t. And note that the properties of this model depends crucially on the value for theta. In the next video, we will consider the stationarity condition for the AR1 model, and we will look at the properties given stationarity. So that's it for now. Thanks for watching.